Good morning and welcome to this webcast. We're glad to have you join us for this STEMnet series. And with me on the screen today, we have a very special guest, Pushpa Ramakrishna, and our host for today's session, Frank A. Gomez. And want to encourage everyone to really bring your comments and questions in throughout this session. I'll be behind the scenes. I'm Jennifer Wicks, hosting from behind, and we look forward to your engagement and discussion throughout this entire session. It's going to be very special today. So thank you again for being here. And with that, I'd like to introduce officially Dr. Frank A. Gomez, our Executive Director of STEMnet at the Office of the Chancellor. And with that, I'll hand it over to you, Dr. Gomez, to get started.
Jennifer, thank you for the kind introduction and welcome everyone for our first webcast of the 2021 new year entitled CSU NSF IUSE program Exemplars. I hope you and your families are all healthy and safe during these challenging times. The fields of STEM hold much promise as sectors of the economy where continued growth in the coming decades is forecast. STEM job creation is expected to outpace non-STEM job creation significantly, reflecting the importance of STEM knowledge to the U.S. economy. The current pandemic demonstrates the need to educate a populace not only to play a key role in scientific discovery, but to provide people with basic understanding to lead productive lives and to distinguish fact from fiction. The National Science Foundation plays a leadership role in developing and implementing efforts to enhance and improve STEM education in the United States. Through the NSF Improving Undergraduate STEM Education IUSE initiative, the agency continues to make a substantial commitment to the highest caliber undergraduate STEM education through a foundation-wide framework of investments. The IUSE, Education and Human Resources, EHR, is a core NSF STEM education program that seeks to promote novel, creative, and transformative approaches to generating and using new knowledge about STEM teaching and learning to improve STEM education for our undergraduate students. The program is open to application from all institutions of higher education and associated organizations. In fact, there are currently 33 funded IUSE projects in the CSU system. NSF places a high value on educating students to be leaders and innovators in emerging and rapidly changing STEM fields, as well as educating a scientifically literate public. In pursuit of this goal, IUSE EHR supports projects that seek to bring recent advances in STEM knowledge into undergraduate education that adapt, improve, and incorporate evidence-based practices into STEM teaching and learning, and that lay the groundwork for institutional improvement in STEM education. In addition to innovative work at the frontier of STEM education, this program encourages replication of research studies at different types of institutions and with different student bodies to produce deeper knowledge about the effectiveness and transferability of findings. Today's exemplars are proven champions in their respective fields, and all are IUSE-funded recipients. Before we begin, I want to remind the audience to use the open chat box on their screens to type in their questions. Our speakers, when not presenting, will do their very best to answer your questions in real time. So let's begin. It's my pleasure to introduce my friend, Dr. Pushpa Ramakrishna. Pushpa wears many hats at NSF, including serving as Program Director in the IUSE, Advanced Technological Education, STEM Scholarship Program, and the Hispanic Serving Institutions programs in the Division of Undergraduate Education. We are fortunate to have her take a little bit of her time out of her busy day with us and to speak on NSF and the IUSE program. Unfortunately, she'll need to depart a little early today after her presentation, but you can always contact her or any of the other program officers with your questions. Pushpa, welcome. It's great having you join us today, and the floor is yours.
Introduction to the program. And it's amazing that you guys have so many IUSE projects because IUSE is, as I said, one of the most meritorious and hard to get program, hard to get funded program. And so today I'll quickly go through a little bit about IUSE, our merit review criteria, and how to prepare a winning and a competitive proposal. To start with, we'll do a video on what is NSF, and then I'll talk a little bit about our program.
Government has a responsibility to see that our country maintains its position in the advance of science. As a step toward this end, the Congress should complete action on the measure to create a National Science Foundation.
For 70 years, NSF investments in people and places have helped build the backbone of America's scientific enterprise. We focus on the large, big questions, big projects. It means taking risks, staying the course, because game-changing breakthroughs don't come quickly.
We have seen what we thought was unseeable.
We focus on the small, where a single piece of new knowledge can advance an entire field or save a life. We are about exploring the world from the top, the bottom, and everywhere in between. We are about big ideas and bold vision. You see the results everywhere. Innovations, marvels, built on a foundation of research we empower. We make the impossible possible. Who are we? We are pioneers, risk takers, visionaries, who stand with the bold at the frontier's edge. And together, we transform the future. We are the National Science Foundation, and this is where discoveries and discoverers begin.
Hi, everybody. Again, I hope that you got a good overview of what NSF is about. And we just finished our 70 years this year. Actually, it was last year was 70, and we finished the 70 years this year. And what NSF is trying to do is to promote the progress of science, STEM, and in order to advance national health and prosperity and welfare, and also to make sure that we are becoming a global leader and stay sustained as a global leader in research, innovation, and education. So, and NSF's budget is about $8.3 billion. And just yesterday, the Congress appropriations came out, and we've got a $0.2 billion extra. So it's $8.5 billion for this year. 94% of all of the money that we gets back into colleges and universities for funding. We get about 41,000 proposals in a given year, and we award about 11,300 proposals in a given year. So it's a huge enterprise, and 1.4 billion of that goes to education. So I'm so glad you're all interested in our IUSE program and in applying for our educational programs. As you know, we have many research directorates, but I belong to the Education Directorate, which is the Education and Human Resources Directorate. And our job is mainly, our goal is to prepare the next generation of STEM professionals and to attract and retain more students to join STEM careers and open this up for all students. So that is what we are all about through EHR. EHR has 4 divisions, and I belong to the Division of Undergrad Education. And as Frank just mentioned, we have many programs, but IUSE is the most signature program. Pretty much every program officer in our Division of Undergrad Education works on IUSE. And please, whatever your discipline is, you can look at the disciplinary contacts, and please contact your program officers in that particular discipline of yours so that you can get more information. I'm a biologist, so if there are any biologists on board, I would love to help you out craft your proposals. As Frank mentioned, the purpose of the IUSE is to promote novel, creative, and transformative approaches to teaching and learning and generate new knowledge about STEM teaching and learning. And when we are thinking about IUSE projects, it could be within your disciplines, it could be interdisciplinary, but Finally, you need to add to the body of knowledge of what truly works in undergrad STEM education. We love to see evidence-based practices incorporated into STEM teaching and learning. So think about those things. And also, we like to see how institutions can change with respect to undergrad STEM education. So when you think of the broad IUs, there's two tracks. One is engaged student learning, where you truly want to know how are students learning and what's the generation of knowledge that is with respect to student learning. And the other track is the institutional and community transformation. How can you change departments? How can you change institutions and improve undergrad STEM learning? And that is the institutional and community transformation track. This is a very busy slide, but it just gives you an idea of the complexity of our IUSE program. On a given year, we get about 1,200 to 1,300 proposals in IUSE. We run about 90 to 100 panels in IUSE, so it's a huge enterprise. So please check the program solicitation for the levels of IUSE and the different deadlines of IUSE. For example, engaged student learning, where you're looking at how students learn, you have from level 1 to level 3 with the different deadlines. And in the same manner, when you're looking at institutional and community transformation, you can go from a simple capacity building $150,000 project to a multi-institutional consortium across multiple disciplines up to $3 million. So there are many, many approaches, and all of those depends on your idea. What is your idea, and how do you think, what is the scope of the idea, what is the purpose of the idea, and how do you think you're going to bring about change, whether it's with student learning or with respect to institution and community transformation. So how do you prepare a competitive project? So you start with your bright idea. So you have this idea, how are you going to communicate to NSF and to the peer reviewers about your idea? And NSF prides itself on two things, intellectual merit and broader impact. Think of your idea in terms of that. What are the objectives? What are the research objectives? What are the questions you might have for evaluation? If you're very familiar with IUSE, in the previous solicitation, we always used to stress on educational research, but the brand new solicitation that came out a couple of years ago, it's not really brand new, it's a couple of years old, but the newest solicitation has the idea of whether you can use educational research or evaluation as a way to generate knowledge. So think of it in those terms and have a very good implementation plan of how you want to craft your proposal such that you can communicate your ideas clearly to the reviewers. So you need to have a very strong rationale when you think of your project. What's the need for the project? Provide a really clear and compelling argument for the need for the project. And you need to clearly articulate the STEM content and make sure that the research design and methodology is well thought out. And then we really like to see a lot of extensive literature review, because the evidence base is very important in writing a good proposal. So when you're thinking of any project idea, always think with respect to the gold standard of NSF. What is the intellectual merit? What is the broader impact? When you're thinking intellectual merit, you're going to be thinking about how are students really going to learn? How will it advance knowledge? And then when you think about broader impacts, you're thinking about how is it going to help society? How is it going to benefit society? And so when you craft your proposal and you turn it in, it is read by a bunch of peers. And I really, really advise you, especially if you're new to IUSE, to contact a program officer in your discipline and see if you can be a reviewer yourself. because when you see the review process, you can better understand the program, as a result of which you can do a better job in writing your own proposal. And the reviewers, pretty much, as I mentioned before, we have about 90 to 100 panels in a year just for IUs, and we are constantly looking for reviewers. So think about that, because the reviewers will always look at your proposal in terms of intellectual merit and broader impact. So there are some helpful hints in crafting a proposal. One of the most important things is to read the program solicitation. I know it's a no-brainer, but still it's so important to do, because when a reviewer comes in and reads your project idea, your project description, they are going to rate it against the solicitation. They don't rate proposals against each other, but they rate it against the solicitation. The other thing is, work on some project that you care deeply about, because if you are passionate about it, it's going to come through. And the reviewers may really look at it in a positive manner. And also, the evidence base is so important. It's important to build on what is already being done and how can you leverage things that are already happening. You need to also think about it in terms of, not just your classroom, your department, your institution, but think more globally. How is this going to impact the STEM enterprise nationally is what you'll be thinking about. Have measurable goals. And finally, in IUs especially, we really look forward to looking at team projects, not so much single PI projects. So think teams when you're submitting IU's proposal. Again, evaluation and then dissemination are important things for the IU's project. Some of the fatal flaws, simple, but many people forget it, is deadlines are strictly enforced. It's always 5 p.m. your time, not 5:01, 5:02. We get so many calls from PI at the last moment saying, oh, my technology didn't work, I'm a minute late. Unfortunately, we do have to have the deadlines enforced. And we need to have all the, the necessary page limits, font size, etc., because you certainly don't want your proposal and your project idea to be returned without a review if you don't follow these things. So please make sure that even though it's simple, you do follow those things. The other thing is, as you're writing your proposal, it's almost like a backward design, like what is it that you finally want to achieve, and that's what your whole project is based on. And then you'll be wondering about what are the methodologies that you're going to use, what's the research design you're going to use, etc., to achieve that particular end goal. So also make sure you have a good dissemination plan, and then your past accomplishments. You may know your accomplishments, but the reviewers may be new to you. So it's a good idea to talk about your prior work, etc. And then please make sure that you do not provide support letters. Some people send letters from congressmen saying that, oh, we support this, but those are not accepted, and sometimes they're even returned without review. If you do need to have a letter, it needs to be a letter of commitment according to the PAPPG guidelines. And so talking about the PAPPG, though, that's a very important document. So you can just Google PAPPG, and that means Proposal and Award Policies and Procedures Guide. And please make sure that you do follow that for the guidelines of the proposal. So finally, in essence, IU's proposals, the real reason for it is that we look at it in terms of potential to advance knowledge, which is intellectual merit. What are the benefits to society? Is it creative? Is it original? Is it transformative? Is your project plan well-reasoned, well-organized? Does it have a sound rationale? Do you have a good evaluation plan and an assessment mechanism that really works. And finally, of course, the qualification of your entire team and whether you have the resources to do the work. So that, in essence, is the IUSE program. I do hope you'll have an opportunity to connect either with me or any of our many 20 plus program officers in the Division of Undergrad Education. And also, you can write like a one-page project idea and contact us, and we'd be very happy to talk to you about it. Unfortunately, I have a IUSE panel running today, so I need to leave. I feel very sorry I'm not here for the whole day with you with the question and answer. But again, I thank Frank for giving me the opportunity to talk to you today. Thank you.
Pushpa, thank you for your great presentation and the great advice you provided to all of the registrants here. And certainly everybody at NSF has been really kind, certainly when I've reached out, and I can certainly vouch for everyone else. So thank you. We all know you have to leave, but certainly you're doing a great service there, and we look forward to working with you in the future, Pushpa.
You're welcome. Bye.
You're very welcome. Have a great day, okay?
Okay, bye.
So let's transition to our next speaker. Is Anthony Rathburn from Cal State Bakersfield. He'll be speaking on using marine science research experiences on land and at sea as gateways to geoscience careers. Take it away, Tony.
Thanks, Frank. And thank you, everyone, for joining us. Today, I want to talk a little bit about a GeoPaths project that I've been working on, where we involve students in hands-on research, both on land and at sea, to help them gain experience and also to introduce them to a wider range of geoscience careers. And I'd like to acknowledge my collaborators, Sarah Gray at the University of San Diego, Dick Norris and Alex Hangstifer from Scripps Institution of Oceanography, which of course is part of UC San Diego. The collaborators and I have been working on getting students out to sea for a couple of decades now. So we have a lot of experience working together. We have a lot of experience in getting those research experiences at sea to students and also incorporating those into the classroom. And so we were able to, when we were putting this proposal together, we were able to push a lot of fundable buttons. So career day events, videos, modules developed by teachers and pre-service teachers, as well as incorporating the data and samples into the classroom and developing curriculum. But any one or two of those projects or aspects would have been made for a fundable project. So we were able to do many more things because of this large template that we had to work with, but those starting out might want to narrow it down a little bit. Our project is based on multiple cruises and multiple different aspects involving students. And of course, our main objective is to recruit minority students into the geosciences and also enhance and increase the oceanographic program at CSUB. Even though we're not on the coast, the ocean encompasses 70% of the planet, so and a lot of interdisciplinary research, so it's an important aspect of geosciences. So a little bit more about the project. We are, when we go out to sea, we're actually conducting real research. So the students are helping to collect real research samples and data from the cruises, the voyages that we take, along with the samples, are not only used for research, but also incorporated into the classroom, into labs, and into modules that I'll talk about in a little bit. And again, we've got a wide range of topics that we cover with the researchers that we have working on the project, from geochemistry to ecology, micropaleontology, and oceanography. And again, the students are active members. They're treated as equal scientists on these voyages. And we were able to also involve students and pre-service students, pre-service teachers, I should say, and teachers in one of the cruises. So we have two different types of voyages. One was during the summertime, where we have a multi-day research voyage involving students that are staying on board and sleeping, working, eating on board and working in shifts over 24 hours. And then we had another weekend set of cruises in the fall, where we were able to go out on 8 or 12-hour ventures and involve a lot more students. So on the summertime cruises, we couldn't involve quite as many students, but we developed mentors from that student population that would then help us mentor and train students on the fall cruises. And that methodology worked out really well. And that's something that we had learned from our template before. And again, having student mentors as part of a project is a good idea. Of course, those of us coming from CSUB, we wanted to make sure that we also took advantage of the area in terms of being able to get students out to tour Scripps Institute of Oceanography and some of the surrounding areas as well. So in terms of the activities, students were involved in teams that worked in shifts for 24 hours a day on these cruises. And I want to emphasize that these are not field trips, they're not labs, they're totally immersive experiences. And they're very transformative because of that. Students are working elbow to elbow with research technicians, with graduate students, with postdocs, with beginning professors, with professors that have been, and researchers that have been out to sea for decades. And so all of those folks are all working together to gather research data and to collect samples. And students were involved from the very beginning of packing equipment, transporting it, setting up the labs. Of course, we have to set up these floating labs on the ship, including tying things down. As you can see here on the right, we've got people working on students working on microscopes at sea, and those microscopes are all tied down so they don't fall off on a rocking ship. So there's a lot of things they have to learn, learning the ropes, safety, learning how to deploy and recover, and they were involved again in every aspect of the science, including the aspect of discovery when we brought materials up from the seafloor. Again, they were working with teams. Here's one example of a team that included teachers, professors and research scientists, graduate students and undergraduates from CSUB and the University of San Diego, all working together as a team, working in shifts and doing whatever jobs that were required during the time that their shift was in operation. As I mentioned, one of the cruises that we had, we were able to involve high school teachers, and they served as mentors for pre-service teachers, and together they put together modules that we will eventually make available throughout the country to high school teachers and to colleges that request them. And these are based on real samples, real data, real experiences that we had on board, and real principles essentially that were learned on board. And one of those, I've included pictures of one of those here on the right. Styrofoam, when you send it down to the bottom of the ocean, all of the air gets squeezed out. And so styrofoam cups, for example, get shrunk down to a very small size like this one, for example. We've got a scale on there. And we've got a number of these that we'll make available in these modules to people that request them through Scripps Institute of Oceanography. We also were able to make some shrunken heads, but we don't have quite a number of those to distribute. We did a lot of different aspects of science, as I mentioned, including microplastics, neodymium, geochemistry, but one of the foci here for student research was focused on the single-celled organisms that are about the size of a grain of sand called benthic foraminifera. They're the organism that I work on, for example, and one of the great aspects of working with these tiny creatures is that undergraduates can be trained to process the samples, to pick them under the microscope using a small paintbrush, to identify the species, etc., and to do all of the research from start to finish, and in this case, actually from collection from the seafloor all the way to presentation. And so that's one of the things that you want to think about too when you're putting together a proposal, is that the projects, the scientific research projects, have to be ones that can be done within the time frame and that can be done by undergraduates, and you are able to train undergraduates within the time frame that you have. And that's, again, one of the advantages here with this particular aspect. And of course also we involve technology. So the foraminifera that you see there in the lower right, those images were taken with a scanning electron microscope. That's also a very complicated piece of equipment, but it's very easy to use, and it's very easy to train students, including undergraduates, to take those pictures. We have a lot of different results, and I don't have time to go over them all, so I'm just going to talk a little bit about a few of the results that we had in terms of the evaluation of the project. So we were able to involve over 200 students, including undergraduates, from freshmen to seniors and graduate students on these voyages so far. We've got more voyages to come up. And our analyses of pre and post student surveys showed that about 50% increase, or about a 50% increase of students indicating that they had a strong professional network in the geosciences. And of course, that was a result of them working elbow to elbow with a wide variety of different geoscientists, from the technician, the scientific technicians, all the way to the captain and crew. And so that's a major outcome of these immersive experiences. And we had a lot of different comments. One of the more common one was that they really like being an active scientist, really being treated like a real scientist, and doing real science as opposed to just sitting on the sidelines and watching others do it. So just real quickly, some of the lessons that we learned: this is an effective method. It's a way to entice and increase student participation in research. And it's also, these field experiences are good ways to build a program. What we've got coming up for future work, we're going to do some more career-oriented activities. We're going to continue our research. When we can get undergraduates back in the lab, we'll be able to increase that a bit more. We've got 3 more voyages. Our voyages this year were postponed because of COVID, but we will be able to get those in probably not next summer, maybe the summer after. But we've got a number of more research voyages to collect more data. So I want to take just a few minutes here to give you a few of my recommendations regarding putting proposals together. And I've listed a few here, but I'm just going to hit a few of the highlights. One of the things that I would strongly recommend is that you talk with experienced researchers. They may be within your university or outside, or with colleagues elsewhere in the United States, but talk with researchers that have successfully applied to the same programs that you're looking at. That's really, really helpful. They can provide significant insight. I would also recommend that you identify your needs early on, and that you then contact collaborators. And they may be folks that you haven't worked with before, but you need that particular aspect in your research project. And I would strongly recommend that you do that early, and that you use all of your colleagues, former students, folks at the CSU, and reach out to UCs as well to fill in those gaps in the research areas that you need, so that you can have the complete project and the complete team that you need for your proposal. And the most important aspect of this, though, is don't get discouraged. Persistence is the key to success. Your proposal might not be successful the first time around, but if you talk to program managers, if you look at the reviews, figure out what might be done to improve the proposal, and be persistent, and don't get discouraged. And with that, I'd like to introduce Resa Kelley from San Jose State University. The topic that she'll be talking about today is exploring how students compare conflicting atomic level animations of chemical reaction events. Take it away, Resa.
Thanks, Anthony. Hi, everyone. So this is, I'm sharing a study that collaborator Sarah Hansen and I have been working on with a team that is Seville Akagan and Adrian Vialta-Cerdas. And the idea behind this project was really that we wanted to engage students to think more deeply about the animations that they were watching. Because a lot of times they'll watch animations, but they tend to just want to spit back what they're seeing without a lot of deep thought. And so the goal was to design videos of chemical reactions that exhibit obvious signs of chemical change, and then partner them with conflicting atomic level animations of the same reactions to get students to think about what evidence they witness in the videos of the chemical reactions, what evidence they would need to select the most scientifically accurate animation that they watch of the three. So we for this proposal, there have been several studies that we've been working on to investigate how students respond to videos of experimental evidence and these conflicting animations. My collaborator, Sarah Hansen, does novel eye tracking studies, and we partner with each other to kind of compare what our findings communicate. I'm a qualitative researcher, and so we're working in tandem on how students think about these visuals. And of course, the biggest goal is to bridge research to practice and to examine how students respond to the tools both in clinical and authentic learning environments. So with that, I thought it would be useful to first go through and give you kind of an overview of a study that we've done. And these are studies that we do in a clinical setting. And so what you're seeing to the right-hand side of the screen is a video of experimental evidence. And I'm going to ask, I don't know if Jennifer, you're able to mute that. Yeah, thanks. When...
Yeah, I don't think I'm going to actually be able to mute it at this point. I'm so sorry.
Okay,
Resa.
No, that's okay. I might just be able to
turn
turn
down the volume,
yeah,
actually,
I'm going to do that.
On the video itself.
Yep.
Okay.
Great.
Okay,
yeah.
Let's see if that'll help. Okay, perfect. Thank you.
Thank you. So what you're watching is a video that we designed to look like the cookbook videos that you might see on Facebook. And the reason we wanted to take that approach was in part because the length of videos can be, too long, and students lose interest. And so we wanted to kind of play up some of the key features to keep their visual interest. And also we wanted to use these videos as kind of reminders of what they've seen in the lab. So these aren't like videos that they haven't seen before. They're videos that they also do in the laboratory setting. Although online it might be that they watched other videos of these kinds of reactions. The other thing that's particularly interesting about this is that we wanted to have places for students to key into controls, such as in the first video, you'll notice that it's distilled water that the wire's added to. The central beaker is where the silver nitrate solution is, which is, for this particular video, we're looking at redox reactions. And in the third video, we're just using a copper-2 nitrate solution that that's kind of there because the end product of the main reaction turns blue in color. So it's kind of to get them thinking like, how come they're both blue? So those were some things that we had in mind as we were constructing the videos. And what you'll notice is that when this wire is removed, we wanted to allow students to see the reaction up close. So at the end, we give kind of a zoomed in perspective, so that allows students to kind of see just a little bit more closely what the accumulation looks like. And so you'll see that coming up. Notice also that we tested the connectivity of solutions because we're looking at ways to kind of apply skills that students learn in the lab. So this is a place where well, that's it. There's other videos that we have that we actually bring in more of that zoomed in perspective. So the next phase of the study is after students watch this video of experimental evidence, they're asked, how familiar is this video to you? And usually they always tell us it's pretty familiar. We've seen this before. But we're also looking for ways that it's not so familiar, and just to kind of see what they're keen into as like, this is new to us. But once they do that, we then take them into the second phase of the study, which is where we look at their ability to construct models. So now you might wonder, why would we want to do this? And the reason actually is that we're trying to scaffold the things that they're going to see in the animations that come up. We're trying to present ways that they can engage with the species that they're going to see, so that's not just like there are a bunch of balls moving around on the screen, which sometimes students will tend to think like, all of these atomic level things just look like random balls moving around. And so we get them playing with what they think is happening and how they picture what's going on with the reactions first, just to understand a bit more about their mental models of these atomic level events. And then we show them the contrastic animations. So in the next slide, so coming up, you're going to see 3 different animations. But this first one, I'm just going to start playing it right away. For this first one, what you'll notice is this is actually one of the wrong animations. Of course, we don't tell them that. And we're trying to get them to think about, okay, what's happening? How does this relate to what you modeled? And of course, a key is presented to the students, so they actually know what substances they're looking at. And in this particular animation, you notice that there's a lot of stuff that just kind of accumulates on the copper surface. In the second animation, again, we're kind of looking at what's going on in solution. So you've got silver ions and nitrate ions, and they're moving around in solution. And it's a little different arrangement or mechanism for how the reaction happens. And then while that goes on, we give kind of a fast forward because we want to kind of just play a little bit of movement and kind of get them to focus on the timeline of certain events. And then in the last video, they have one more comparison to look at. So this video, this animation, is actually modeled after a single replacement reaction in terms of how you might map the equation onto the atomic level, which we find that a lot of students do. They might not have well-formed ideas of what the atomic level is like, and so they oftentimes will picture the reaction to look like this one. The first one actually was based on a study that we did, a pilot study, where we found that students, when they saw the solution at the beginning, they tended to think that everything in the solution just ended up on the wire. So we wanted these 2 possibilities because they relate really well to what students tend to think about, and we wanted to get them to notice how there's differences between the animations and to start to question what they're seeing. Like, why might it be this one? Why not this one? Those are the kinds of questions we want them activating as they go through this. So in the third part of the study, we actually allow them to go back to the models and we ask them, all right, how do you make sense of the animations? And would you like to revise the model that you initially constructed? And so we're looking to see what things they take in from the viewing situation. So when we embarked on this study, one of the things that, again, we were really keen on doing was developing our students' ability to critique models and to be more critical consumers of the information that they are presented with in science and then in life. And so one of the big findings from this study is that when students select the animation, they're actually looking for the animation that fits with what they modeled, which I guess isn't too surprising. But then and usually they don't see, like they tend to, there's always some aspect of an animation that just doesn't quite fit with what they modeled. And so then they kind of move into a contradiction and reinforcement phase. So if the evidence is contradicting, they have 2 ways that they might go about dealing with it. One, they might just dismiss it and say, no, that information's wrong, I'm right. And that happens for some students, but then there are other students who actually begin to question what they believe, and they will accept and modify, and they're usually the ones that do the revisions. With students that they see information in the videos and it looks exactly how they pictured it, a lot of times they'll tell us that it strengthens their beliefs and makes them feel more confident. So the big take home from this is that students do learn how to critique and that they do think much more deeply about the concepts, which I think in this online environment is really important to many of us. And so some of the changes that we made based on this study is that we realized that with the animations, we needed to make more explicit connections to the macroscopic level. So we actually changed our animations up so that we could show kind of a presentation of the model, and then we connect to the atomic level world. We also provide kind of a built-in key to the animation, which you're going to see coming into the side, and we give indication of like the conductivity measure that they saw in the video. This is what that conductivity measure was, and now does that fit with what you're seeing in the video? We also made sure to choose a colorblind friendly color palette so that it's visually distinctive for all of our viewers, and that's been pretty useful as well. So these are some of the changes we made as a result of this study, and we've got all of these videos are available online on YouTube. If you search for my name, you're going to be able to find them, or if you go to my San Jose State website, you're going to find them there as well. So I mentioned at the beginning that we work on making sure that we bridge our research to the practice. I actually showed these animations in my fall chemistry class as well as this semester. But these are some clicker question results, which shows you again that in class they were a little bit, well, actually it fits quite well. The first animation was the accumulation buildup, and then the second one was the most accurate animation, and the third one was the single replacement. And you'll notice that they're usually between those two animations, and they have great conversations about like, why do we decide which ones to pick? And what's interesting with this particular situation was that after they collaborated, because they were asked to first vote independently, but actually after they were asked to collaborate, what you notice is that some of them actually made wrong decisions and chose the animation that looks more like the single replacement reaction. So again, this leads to a lot of great conversations, which is what we want. So I thought I would summarize and give you kind of a quote from a student who said, "I don't know if an animation is chemistry, if that even matters. It's just this extra step that I see in my head that I'd like to see. So seeing the first animation, it's just an instant thought. You see something completely different from what you have, and it makes you question yourself." And I thought that really embodied a lot of what many students experience when they're watching the animations. And so in closing, I want to say that in critiquing contrasting animations, we know that students are going to make good decisions, and sometimes they will also make poor decisions. But what's really important is how students engage with the animation and try out ideas that is most important in developing students' ability to think critically. And that's what we want to see. So again, just thanking my collaborators, Sarah Hansen, Seville, and Adrian, the animation artists, Mina and Jake, and all of the other people as well. So I'm really happy for their work, and also thanks to the National Science Foundation. All right, so that's my presentation, and next I would like to introduce David Brookes from Chico State. He's going to be talking about an invitation to engage in undergraduate STEM education at NSF. David, take it away.
Thank you, Resa. Thank you, everyone, for coming and listening to our talks. So first I'd like to situate myself. So there's a growing movement of discipline-based education researchers, or DBER people. We're people who do education research but situate ourselves within the discipline rather than the school of education. And this has resulted in an acronym soup of PER, Physics Education Research, CER, Chemistry Education Research, and so on and so forth. And I am a physics education researcher who resides in the Department of Physics. So I want to explain the title of my talk and the motivation behind our research. I want to start out by introducing you to the investigative science learning environment. The primary goal of the IO approach is to engage students in the process of doing physics by having them engage in authentic epistemological activities and practices of actual physicists. By this I mean the knowledge-generating activities. And the outcome of this approach, in addition to learning about physics ideas, students develop scientific habits of mind or critical thinking skills and a more deeper and more sophisticated understanding of where knowledge in physics comes from. Okay, so we need a model of this process, And I don't have time to sort of delve into it in detail, but you can read more about our research in any of these publications. The key thing I want to highlight here for this talk is that the IO approach is centered around experimentation, and experimentation plays three key epistemological roles in physics. The first is observational, in the sense that it provides new data that needs explaining. Testing, in the sense that we test our explanations and try and rule out the wrong ones. And the third is application, in the sense that we can take our physics knowledge and apply it to do something meaningful in the real world, like build a bridge or whatever. So as I mentioned, our primary goals, we want students to develop scientific habits of mind, or scientific abilities as we call them. But firstly, we need to identify what these scientific abilities are. And so here's a short list of some of the scientific abilities that we identified through our prior research. And the important thing, of course, is that we need to be able to measure them. So back when I was a graduate student, we developed a set of scientific abilities rubrics, that's a reference in this publication below, that allow us to reliably measure whether students are developing these scientific abilities through their engagement in the process of doing physics. Okay, so in preparation for this talk, Frank asked us to share our knowledge and experience about writing and executing a successful IUSE grant. So a lot of what I'm going to present is going to sort of focus on the writing and design of the research project more than the outcomes of the project. So I want to start out by echoing what Pushpa said, which is that one of the advantages of being at a CSU is that it allows me to approach research slightly differently from a traditional R1, in the sense that I'm not in this pressure to write grant after grant, and so it allows me to think about big questions that keep me awake at night or get me out of bed in the morning. And one of them is basically born out of the frustration by how poorly we use computers in education. And so one of my big motivations is the question of how can we use computers and the internet to enhance student learning. So there are things that computers can do that are better than real life, and so what are those, and how can we exploit those to enhance education? The second thing, of course, is it's maybe obvious, but don't do it on your own. Assemble a great team with diverse skills and expertise that complement your own. And so here is our research team. Okay, so the next thing is have a plan. So what happened with this grant is that Matt and Peter, two of the people on the previous slide, actually approached myself and Eugenia Etkina. They had created this amazing video environment that you see on the left side of the slide, and they call these direct measurement videos, and here students have access to a pull-down menu of overlaid HTML5 tools that you can actually overlay on the video of the experiment, and you can measure stuff. You can measure distances, you can measure time, you can measure angles. So they have this toolbar that they can pull down, and then and so they approached us, and I forgot to mention, of course, and you can also change parameters down at the bottom. Or if you look at this thing down at the bottom, you can actually pull up new videos that change the parameters of the experiment. And so, Matt and Peter approached us, and they saw that their environment was a great fit with our epistemologically authentic approach to education, and so the idea of this project was born. And basically, can students develop scientific habits of mind through video-based experimentation? And so we had a basic design. We will test it. We'll design these environments. We will test them on students at Chico State, and we will disseminate them to implementers who will report back on how they were using them. So that's the project. Okay, and this is a way too busy slide, but I did want to put this in here. So this is the tip that I learned from my mentor, which is, if you're writing a grant, write the first 2 pages. So, and see if you can write the entire grant in 2 pages, and make sure you address the following things. So first of all, the challenge. So what's the big question that you want to address? Then our response, you can phrase it how you like, but it's like basically this is a thumbnail sketch of the grant. How are you going to respond to this big question? Third, what are you going to produce? So sort of, can you articulate the things that will come out of this thing? And finally, can you address the intellectual merit of the proposal? And so this will enrich the field of science education and curriculum development and virtual learning by XYZ. And finally, the broader impact. This project will benefit society by XYZ. So if you can write, so basically we wordsmith that first 2 pages, and once you can do that, the rest is cake. So on to our actual project. Here is the first stage of the project was to design these learning cycles in a video-based learning environment, and so there are a couple of examples linked here that you can take a look at. And so we designed and pilot tested these and created 5 complete learning cycles on Newton's second law, Newton's third law, momentum, springs, and mechanical waves. And so those are freely available. So the next stage of the project was we did this quasi-experimental design where we implemented these video-based labs in a 96-student algebra-based physics course at Chico State. And this was the rough outline of the design. In the lab sections, one lab section did all video, one section did all apparatus-based, one section did all video-based, and then the 2 counterbalance sections where they did 2 apparatus and 3 video, or 2 video followed by 3 apparatus. And there we collected a large amount of data at the end. We collected their lab reports. We saw how they performed on common exam questions, and we gathered two sources of attitudinal data, the ECLAS and a flow survey designed by one of the members of the team, and of course video analysis. That's my specialty, is qualitative data. So there you go. So here is the sort of answer to the research questions. The first research question was basically, do students actually learn physics equivalently from these 2 different formats? And so we embedded these exam questions. We scored them on a common rubric, and the short answer is, okay, we did the implementation twice in the fall, first in the fall 2018, then spring 2019. We found that indeed they're across the board in all the key topics that were covered in these videos, that the apparatus-based students and the video-based students learned the same physics to the same degree. Then the interesting thing, of course, the core research question, which is the title of the talk: do students develop scientific habits of mind through video-based experimentation? And this is where it gets kind of interesting, because for the most part, the 2 groups developed roughly the same scientific habits of mind at roughly the same levels of performance on the rubrics, on the scientific abilities rubrics that we used to score their lab reports. But there were a few examples of things that were starkly different. One of them is experimental uncertainties, and this is a case where the apparatus-based students far outscored the video-based students. And we kind of had the suspicion going in this would happen because videos have certain affordances, but they also have certain constraints. And so, one of the constraints is you don't have the same experience of messing around with noisy data that you do with real physical apparatus, and it kind of shows up in their development of their ability to handle experimental uncertainties. But on the other hand, one of the affordances of video is that it allows you to gather very clean data. And so we can see this, that the students in the video-based group are much better at acquiring and reporting nice, good data that could be used to discover physical relationships, for example, in this case, examining the relationship between acceleration and force and acceleration versus mass. That's to build Newton's second law. And so, in conclusion, the sort of big takeaways of our project are that students do develop scientific habits aligned through video-based experimentation, but there are some interesting affordances and constraints that come out of the two approaches, and something that I do not have time to report on, but one of the sort of big takeaways from our attitudinal surveys that we found is that students enjoyed video-based experimentation a bit less as compared to apparatus-based experimentation. It wasn't like they hated it, but there was a significantly lower amount of enjoyment across the board, and that has resulted in a very interesting investigation into how scaffolding happens and how people collaborate when using videos versus apparatus. And that is the end of my talk. I'd like to introduce Janet Bowers and Bori Mazzag, who will talk about math faculty collaborative with client disciplines to improve lower division.
Thank you very much. Appreciate it, David. I am Janet Bowers, and I'm the PI.
And I'm Bori Mazzag from Humboldt State.
So our project can actually be summarized using this question. And I know so many of you are STEM faculty and other faculty that have math as a prereq. So take 2 seconds as opposed to a minute here and think about what math understanding skills do you want your students to have as they enter your higher level classes. You don't need to write it in the chat, but you can if you want. That would be great. So in the interest of going way over on time, I can tell you that this question was first proposed by members of the Math Association of America. And this was done about 20 years ago. And there was a bunch of workshops led by various mathematicians asking client disciplines if you had to develop the kinds of students that you, the kinds of topics that you wanted, what would your students need to know in terms of math? So the result of this was a discussion based on a group of people. They spread these ideas in 2 volumes. As you might guess, these 2 volumes have a bunch of answers to this question based on input from the faculty. And it turns out that although there was 2 volumes worth of work, they can somehow be summarized to say conceptual understandings, ability to read and interpret graphs, and to use and understand data and patterns, and the ability to use technologies. So in order to promote the spread of these ideas across math departments, in the US at least, a group of faculty received the NSF IUSE award called Summit P. This is an awkward acronym, but it stands for a national consortium for synergistic undergraduate mathematics via multi-instructional interdisciplinary teaching partnerships. And you can see in those words that those are very similar to what Pushpa was talking about. So the idea is that we are a group of 12 universities, and we have a combination of small and large, public and private. Some teach online, some teach in person. And we think that there is great strength in the diversity of these different sites. So you may ask, well, how does the grant organize this wide and varied group? And the goal at each of these sites is to reach out to the partner disciplines. And so the team has collected and honed 4 tools. And this process is some of the best practices that we have found as a way to work with we meaning math departments, to work with partner disciplines. So the first one is fishbowl discussions, and Bori is going to talk about that. The second tool is FLCs, and I believe actually that the next speaker from San Marco is going to talk a little bit about that, but we'll also mention FLCs, which is faculty learning communities. The third is site visits, where one or more university teams visit another. And perhaps most impactfully is the creation of truly interdisciplinary activities that have authenticity and immediate application in subsequent classes. So the results from SDSU have been basically honing and figuring out how to use those tools to collaborate with different folks. We have been redesigning two math courses, pre-calculus and calculus for the life sciences. We received help from biology, chemistry, and physics partner discipline faculty. And the outcome of our work has been new pre-calculus labs and a completely redesigned biology course. And we've collected data on students' views about the labs, and we also collected students' views about mathematics more broadly as part of the data collection for the entire group of institutions. So that is still being analyzed, but we were hoping that we would see more and more students be excited about math as more interdisciplinary activities are used. So now Bori is going to talk about her work at Summit P at Humboldt.
Thank you, Janet. So Humboldt State joined the Summit P Consortium as a second wave of institutions. So our first involvement was in January of 2020, but HSU has already had interdisciplinary collaborations. So we were building on an existing first-year place-based learning community that had many theme-linked assignments. So these were examples of the sort of interdisciplinary work that we were hoping to introduce in mathematics. And our goals were to revisit content and make sure that the skills and the technology needs of the partner disciplines were respected by our mathematics courses, and we wanted to create closer collaborations. The two disciplines that stepped forward to work with us were our environmental resources engineering and our physics department. And together we have determined that two of the courses that we would focus on would be trigonometry and calculus. So some of the other introductory courses in our STEM sequences were already targeted by the place-based learning communities and already included some materials that were interdisciplinary. These two courses have not been yet. So with both of the departments, we used the fishbowl protocol that we were introduced to through the Summit P collaboration. And essentially these fishbowls are gatherings in which we ask the partner discipline faculty to discuss a number of questions that we pose to them about what skills, knowledge, technology they want students to learn in the math classes, and the math faculty are simply observers in the process. So that allows the faculty of the partner disciplines to discuss freely and sort of have a conversation that the math faculty simply listen to. And we found this very impactful. We ended up developing curricular content, and essentially the idea was to motivate the content with examples, hands-on activities, and use some computational tools. We ended up, of course, offering these courses for the first time this fall, and we needed to shift our thinking a little bit to make sure that we were accommodating the online setting. So we ended up having activities that were implemented online in Desmos, and we designed projects that were initially meant to be projects that students would be doing in class, but instead we ended up using a Vernier video analysis tool to do the hands-on sort of data collection, and then we also used a data-based lab using Excel with HSU solar panel data that was illustrating integration. In terms of outcomes, we have collected survey data from the students about student attitudes, and we're preparing an MA focused publication. Obviously, we still have a lot of work ahead of us in terms of institutionalizing the changes and continuing our assessment. So I wanted to talk briefly about the lessons learned. So in addition to, of course, creating the interdisciplinary content and engaging students, like Pushpa said in the beginning, IUSE grants have this goal of institutional change, and indeed that is a broader goal of the Summit P consortium. And the structures that seem to facilitate this best were visibility on campus, so the fishbowl protocol that we used, or the faculty learning communities Janet mentioned, and the campus visits were all activities in the grant that allowed this to happen. It is essential to have administrative buy-in, as you guys probably all guess, and campus visits are a good way to ensure that involving administrators in those visits. We also found that fostering a culture of understanding and an interdisciplinary approach is really important. And again, that is something that is facilitated by the fishbowls and the faculty learning communities. Some other lessons that have come out of our work are that collaboration is, of course, a huge benefit to everybody involved, but it is also very difficult. Often just even making sure that you're speaking the same language with your collaborators can be a challenge. Tenure track faculty involvement and commitment is absolutely key for the success of these projects and maintaining and institutionalizing the projects. And finally, I think it's important to point out that there is a huge reform movement in math education, and of course, with the rise of data analytics, many of these quantitative fields, mathematics, statistics, and data analytics, provide huge educational funding opportunities. So we wanted to say a few words about next steps and long-term plans. So both at HSU and at San Diego State University, we're thinking about sustainability and also opening towards new directions. So for us, sustainability essentially means thinking about how the course content can be passed on to other instructors and how we can disseminate the materials to other instructors. And the new directions involve using the fishbowl protocol to talk to other partner disciplines and then look to further IUSE funding.
All right, let's see. We just want to make sure that your mic is unmuted, Janet, here. I know it was important to have both of your mics, only one unmuted at a time, so I'll hand it back over to you here. I'll go ahead and unmute, and you're open now.
Thank you. And now I'd like to introduce Edward Price from CSU San Marcos, and he will be talking about community transformation through online faculty communities.
Great, thank you. I'd like to start off with a couple questions that motivate my work here, as well as I think important considerations if you're preparing an IUSE proposal. And one, I think most fundamentally, is to ask what will be the impact of the NSF's investment in your project, and particularly how widespread will that be, and how deep and substantive and sustained will it be? Particularly if you're developing some sort of an innovation, curricular materials, new techniques or approaches, how would you support adopters who want to use your materials or your approaches? And especially, how would you provide the kind of sustained, what I will call and talk about more in a little bit, people-based support for them? And as you think about conceiving of a project, where will you put your effort in the initial development work, in dissemination, that is sort of getting the word out, or really in propagating and supporting a sustained use of your materials? And clearly the relative emphasis of those would depend on what stage the work is at.
of course, but I think one of the arguments I want to make is to think about those latter stages, dissemination and propagation, particularly even at the outset. If you are trying to promote community transformation, which is, obviously that's a track within IUSE, but I think even development type projects may also have some community transformation efforts. How are you going to accomplish this, and especially how are you going to do that across distributed participants who might be geographically separated? And so just to, a few opening comments on this, I think, is that it can be easy for us to focus, I know for myself, to focus on building something, right? Developing an innovation, and that's a really fun intellectual challenge that's often born out of our classroom experiences. But if we don't give enough attention to how this would be sustained, how it would help others implement this and build a community of people who are using our approaches, then its broader significance and its impact and reach will probably not be as extensive as it could be, right? And it's important to remember that making a change, especially in your educational practice, is really hard. And if we're asking others to do that with materials that we may have developed, we're asking a lot of them, and we need to think about how we can support them when they do that. One of the approaches that has been very influential for me is the propagation paradigm developed by Charles Henderson and his collaborators, and I encourage you to take a careful look at this. They have a site, increasetheimpact.com, with a lot of materials. They talk about teaching practices as embedded within successive contexts of an individual, in a department, in an institution, and more broad extra-institutional context. In this diagram, they're showing current teaching practices on the left, and then some desired teaching practices that are presumably different in important ways on the right. And the bridge between those consists of these three connected pieces of development, dissemination, and support. And an important point that they make in their work is that support, and particularly ongoing support, is often not as centrally included in efforts to develop instructional innovations and to propagate those. So they in particular call attention to support of many varieties, and this is kind of a taxonomy of them, I guess, in some sense. So they talk about support provided by the project team or provided externally, and they talk about support that might be materials oriented. So you can think about developing curricular materials, developing websites, and those type of things, versus people oriented, where you might have workshops or you might have faculty communities. And in particular, what I want to talk about are faculty communities and work that we've done on faculty communities that take place in a virtual space. So we call these faculty online learning communities. They support faculty in implementing research-based instructional strategies, in becoming more reflective practitioners, and in building community. Some of the key features of folks are that they are long-term. They could be a year. The one I'll tell you a little bit more about is in its 4th year right now. And participation in these takes place at the same time that faculty are teaching. And so you get powerful support from colleagues, and it's very timely. Often if you go to a summer workshop, I've had this experience, I get very excited about something, but you come back into the classroom, and when you really encounter some of the challenges, or you're really trying to understand how to make this work, you're no longer connected to that support. There are also these folks are distributed and virtual, and one thing that's very powerful about that is that you can get a critical mass even if you have a specialized audience. So normally if you only had 1 or 2 people that is your potential audience at an institution, that might not be enough to really form a community. But if you can draw those 1 or 2 people at an institution from many institutions around the country or the world, then you can have a much larger community. This also is a way, I think, that can effectively reach contingent faculty. It has in our project, and others who may lack access to, may easily lack access to professional development or to a professional community. I gotta let this dog out, he's very needy, but I'll just say also this is based on research, including the research by Charles Henderson and his group. Sorry, yeah, so work from home life. The folk that I'll tell you about is called the Next Gen Pet Folk. This map, something was lost in the translation of this map through various versions of PowerPoint. It's supposed to show the whole U.S. and show you that we have about 50 faculty distributed around the country. Those 50 faculty are broken into smaller groups. Each group has some experienced faculty who act as leaders and conveners. And as I mentioned, this has been going on now. We're in our 4th year. I won't say much about NextGen Pet except to give you a little bit of context here. It's a curriculum, a guided inquiry curriculum for future elementary teachers. Primarily, it's also used by some instructors as a general science curriculum, a general education curriculum, rather. Its content is the physical sciences. And it is very rich in student conversations, small group and whole class discussions, students doing a lot of hands-on work, making presentations to each other. So there's a lot of evidence of student thinking that instructors can access, and of course it's very challenging to implement. And so because of that, the faculty really benefit from ongoing support as they teach this course. And the way that that takes place is in these small groups of about 10 faculty meeting every couple of weeks on Zoom. And the discussions center on challenges that people are having in their teaching and troubleshooting those, sharing information and resources, sounding ideas off of others who are teaching similar courses, and supporting each other. And faculty are able to explore pedagogical concepts, but in the context of their classroom practice. So it's not a theoretical discussion that's disconnected from their teaching. It's very much grounded in that. And in combination with these live Zoom meetings, we also use Slack and we use Google Docs, which support communication sort of asynchronously and in between these meetings. And that's been a great combination for us, actually. So to give you a sense of some of the impacts of this, there's a lot I could say here, but to hit a few highlights, members of the folk describe benefits around the pedagogy, their time, and also the sense of community that they're developing. So we asked them about their experience, and they report, moderately or to a large extent, the vast majority having incorporated ideas from the folk into their teaching. So things that they're discussing are making their way into the classroom. That they've developed their skills as a teacher more efficiently than they would have without the folk, and that they've saved time in preparing and implementing their course. And I think that's an important outcome because, of course, participating in this community does take time. And while faculty, I think, feel that it is very valuable to be part of that community, the fact that their time is sort of repaid in some efficiency, I think, is very helpful. And then lastly, overwhelmingly, they report having gained a community that supports their teaching practices. And I think this may be the most important outcome. It is a little ironic, perhaps, but even though an important part of our professional responsibilities involve teaching, we don't always have a lot of spaces for substantive discussions around our teaching. And this has been something that has been a theme in everything we've heard from our participating faculty, that's just very important to them. One thing which happened last spring, of course, was that we all had to move our courses online. And having this community at that point was incredibly valuable for the faculty to share ideas with each other. There were many challenges in teaching a guided inquiry course where students do hands-on work and they have a lot of small group discussions and whole class discussions. And how do you do this in an online format was not an easy thing to reconceive. And the faculty and the community shared a lot of ideas with each other. Eventually, we had a number of them host webinars for the rest of the community and ultimately write up their work into this resource guide. And so I think that that illustrates some of the power that a faculty community like this can have for its participants. I'll just close with a couple of conclusions about folks. I think this is a model that provides ongoing support through participation in the community to faculty, and that can be effective at connecting solo or isolated faculty and allow you to have a critical mass even with a pretty targeted effort. The faculty in this community report increased knowledge and use of pedagogical techniques that align with the research-based instructional approach of the curriculum that they're using. And they have the opportunity for troubleshooting, sharing ideas, and receiving encouragement through challenges that they're facing. If you're preparing an IUSE proposal, I would say, think carefully about dissemination versus propagation and begin planning for that from the very outset. Too many excellent projects have been funded that have resulted in great materials, but which kind of sit on a shelf and aren't used as widely as they could be. And so you need to think about how to increase the impact of your work. The Cal State system is a great venue for dissemination, and I encourage you as a member of the system to really think about how that could play a part in your proposal. If you're interested in folks or folk model you think might have a role in your work, I'd be happy to talk with you more about that. So thank you very much. At this point, I'd like to introduce Scott Kelley.
Thank you, Ed. It's great to be here. So today I'm going to be talking about a project that I was funded to do on engaged student learning and development of active learning bioinformatics education apps for mobile technology. So the project, just an overview of the project and what bioinformatics is. It's essentially the use of computers and algorithms to perform biological research. And it's become increasingly critical to the biological sciences. And I'll just give you an example that the COVID-19, after it was sequenced, originally DNA sequenced, the rest of it for understanding, and I think this happened probably within a day, we identified it using computers through bioinformatics. So we identified it as a coronavirus, we traced its origin and spread, we found new strains, and we were able to determine the structure of the protein sequence itself, all using bioinformatics. And this was done incredibly rapidly, and it continues to be done all across the globe to find new strains before. If we had to rely on bench work for this, it could take years or decades to get all these things to even grow. So it's been a huge, important need. And there's a growing need of it in industry, academia, and public health. But biology students who really understand or should understand the biology part tend to have limited computer experience, and they often actually actively avoid computers or math or such things. So one of the ways that I was trying to enhance their understanding of bioinformatics, of the principles behind algorithms, was to develop these web-based apps that will allow the students to learn the fundamentals of particular algorithms and be able to practice them a lot. And so you could find these apps right now on your device. If you just go to kelleybioinfo.org, you'll see this website, and Kelley is with 2 E's. And the other thing that I developed and worked on with some colleagues was these anticipatory learning modules that help understand the algorithms before they start using them and hopefully increase learning confidence. So the first aim of the proposal was I'd already started to develop these aims, but was to finish the develop of the apps for key algorithms for bioinformatics, fundamental ones like sequence search algorithms. And then I was developing companion puzzle-based anticipatory learning exercises, which I'll show you an example of in the next slide. The second aim was to develop a real-time monitoring software so that when you're in the classroom, you can actually monitor the progress of the exercises in real time as they're doing them in the class to see how people are doing. And then the idea was to add some visualization tools to see this progress, like is 50% of the class done, did I get it right, and so forth. And the third was to develop and implement assessments to determine the effectiveness of the apps that I created. So the results so far is that I've finished developing the testing and debugging of the remaining apps. So the site is really well working. I've actually completed finished the completion and implementation of the anticipatory learning methods. I've implemented a database for real-time tracking that I've used for data collection to see how well the students are able to get this, and then try to correlate that with, say, their test scores. I've also published a textbook on this, but the website itself is free, so anyone can use the website. I just found that people weren't using it, so I thought I needed to write a book to explain it. I have also completed a quantitative analysis paper with a doctoral student and a professor of math education, which was really a useful thing to do. And we've submitted a manuscript which should have already been accepted for publication, but for some reason it's not there. So I wanted to give you an example of an anticipatory learning module and the actually interactive app. So this is actually an algorithm called the BLAST algorithm, and it really is a fairly simple algorithm, or simple idea, is that you have a DNA sequence and you don't know what it is or where it came from. You don't know the gene and you don't know the organism that came from. So an example might be I took a sequence of some infection from someone who was sick and they looked like they were coughing and everything, and I sequenced the DNA, or in some cases RNA, but let's just say we're going to stick with DNA. So I sequenced the genome of the organism, and then I'm like, well, all I have is a bunch of letters in a computer, so I want to know what this thing is. So I put it in this algorithm, and it matches to everything sequence that has ever been sequenced right away, and it brings back a result, and I find out, oh my gosh, it's coronavirus, and it's related to SARS, and it's probably from a bat. So that's exactly the kind of thing that's happened. So I wanted the students to understand this process. And so the first thing I do is, in this process, is I actually do not tell them how it works. What I really give them is what I call a anticipatory learning exercise. And what this is that I give them a problem that I have a mystery sequence, and I have a sequence that it might be a match to. So this is the Q and the S here, query and subject, and this is actually what the BLAST output looks like. And then I want them to say, well, do these things match, and how well do they match? And so the idea is that it's a puzzle that I don't tell them how to do, but it's simple enough that they could probably come up with some kind of the solution to this problem. And I give them a DNA one, and I give them a protein one. It really doesn't matter. What is important is that they see the students here. These are the answers the students gave. And the answers that they gave they found some matches, areas where they looked at it and they said, huh, this part looks like this part looks like that, and I'm going to match them together. And you can see the students did it in different ways. One took a big stretch and looked for a long time, and another took little pieces of it. And then what I do is I take this and I say, okay, come up to the board, and maybe volunteers or people who are interested could come up and show us how they got their solution. So I would take them up to the classroom, and they would present how they got the solution. And often it was different, or it was really interesting how they came about it. And then what I do is I try to translate that solution that they came up with themselves to what actually happens in the BLAST algorithm. And the idea is that they come up with themselves. It's very similar, usually, to the solution that is the actual solution, which means that they understand it from their own principles, their own feelings, and they have confidence that they could have come up with something like that themselves. So the idea is like it is possible for you as a student, knowing very little about this, to actually come up with an algorithm that is very similar to what actually is there. And the cool thing is, often they came up with a new solution or a new idea that hadn't been seen before, depending on the algorithm. So that was the basic idea. That's probably the best part of the whole grant. All right, so the lessons that I learned from this grant was that the interactive learning apps and the anticipatory learning worked extremely well in and outside of class. So they were able to get a lot of practice on this, and they were able to learn how they related to one another. The study showed that the students were able to derive the principles of the algorithms by themselves or in the group exercises pretty well, and they had confidence that they could do it. The major improvement that I made in this was encouraging to share their answers with the class, because this all increased participation and discovered new solutions, and they were really proud, actually, quite of being able to do this, which was fun. The key of the students really felt that they could do it themselves, and I kept emphasizing it. This isn't a mystery. This is something you can do. The other things that I learned was that having a full-time web programmer, or at least part-time, is vital, and I must have someone who can collaborate with me in developing the website, because that was the huge amount of the work. The other thing I found was that databases in real-time implementations were really difficult to implement with lousy Wi-Fi infrastructure. So we had a lot of trouble going back and forth with the databases and updating them in a bad room where you don't have the right infrastructure. So I found workarounds to that made more static images. And then it was more about the sharing in the end than anything, especially with the anticipatory learning. So, but it was, you know, it was a reality check on the technology. So the next steps would be expand the study in 3 ways. First, I'd like to go to larger studies across larger campuses if I could find other people interested in bioinformatics, and try to see if we can implement the anticipatory learning and with especially those exercises. I'd like to focus with the impact on non-traditional CS students. Is this an entry point into computer science? I have a lot of students, especially women, who haven't taken any CS, and they go through the course, they haven't done algorithms, and they turn out to be brilliant at it. They just needed something that they're interested in studying. And they found that biology, they like biology already, and they found that it was really great for them to do bioinformatics in this way. I want to expand the ALN interactives into new areas, especially math or statistics or CS. And the key, I believe, is that it has to be a puzzle that is solvable by the student without very much foreknowledge. And so any kind of puzzle-based algorithms in different fields can be really helpful in having them come up for it by themselves and really help them understand it. I'm going to drop the real-time assessment for now. It's just so much work. I don't think it added a lot to it, but I can work on that. I'm going to focus on new algorithms and the idea of confidence and testing whether it really gives you confidence, and see if it leads to generalizable thinking about algorithms so they extend their knowledge to other things. I'll definitely need a bigger study with more money for programmers and a better assessment plan. I need I had a qualitative assessment. I'd like to do more of a better quantitative assessment plan. I want to involve the students in designing the exercises, and I want to better connect the theory to the practice. So I think as a larger grant goes, this has a lot of potential. So in summary, it's a very promising start from a pilot. I built a strong, solid infrastructure. I generated new ideas and hypotheses for future grant studies. But I do need to collaborate more broadly with other disciplines, and I think the algorithmic part of it is the key that would help me go to other disciplines and work with other people. And I do need some, but the NSF reviewers really appreciated the creativity and the technology innovations. And finally, I do need a better design and a more comprehensive assessment plan, which is something that I'm definitely not an expert on, so I'd love some help on that. Okay, so with that, I am going to introduce Carol Hood from CSU San Bernardino.
Hi, thanks, Scott. I'm going to build on the conversation that Ed Price started just a few minutes ago. So our project, let me flip our slide here so we can see it. There. Our project is known as the Issues X project. Issues X stands for Investigating Student Success Using Evidence-Based Strategies. First, I'd like to highlight our project team because this is absolutely a project effort, a team effort. Sarah Calori and Laura Whitney are both in the physics department with myself. Mike Chow, Tony Metcalf, and Becky Talon are in biology. Kim Cousins is in chemistry, and Sally McGill is in geology and now the dean's office. We also work with an expert, Karen Serwin, who works with WestEd K-12 Alliance. She's been in the K-12 realm for many years and has been helping assist us at the university level. And lastly, Kirsty Fleming and Kim Costino were both formally on this project back when they worked at CSUSB, but they've branched out to other CSUs more recently. So we started this work many years ago, initially with an NSF wider pilot grant, and now continued it with this current NSF IUSE grant. The goal for us has always been to improve our student learning, and therefore the success rates and graduation rates for our students studying in the STEM fields. Since our student population at Cal State San Bernardino is more than 80% first generation, many of them are come in unprepared for certain fields, math, science, study skills as well. But what we're focusing on in our work is how faculty members rise to the challenge of bringing them up to the level of preparedness that we'd want them to be. So we're focusing on coming to them instead of making them necessarily come to us. Our student population is about 60% Hispanic Latinx, so there's a particular emphasis on for us on that population, but other traditionally underrepresented populations as well. We aim to accomplish these goals using a community of practice model. So this is based on the work for us with a little bit more structure using faculty learning communities, similar to what Ed discussed. The idea of the community of practice is based on the work of Wenger and consists of a collection of people that have a common interest. So this model has been used in businesses, companies. It's not necessarily just an academic idea, but we're applying it to our academic setting. Within the community of practice, participants create, share, and apply their knowledge through their various expertise in order to reach whatever their common goal is. For us, that common goal is improving our students' learning. The community of practice forms naturally with people moving out while the work progresses, and it's basically a very organic process. The community of practice itself may have structured subcomponents like our faculty learning communities, but a successful community of practice will allow for new people to join in and for others to leave when they feel it's necessary to do so without sacrificing the success of the overall community of practice. So as I mentioned a moment ago, we use faculty learning communities to provide some organizational structure within our larger community of practice. These communities can be based on a faculty member's role within the university, and in some cases are specific to the types of classes they teach. We originally planned 4 main types of learning communities, one for our new tenure-line faculty, one for STEM faculty, and I'll talk a little bit more about that in just a moment, one for our College of Natural Science chairs, and then one for the project team of facilitators so that we can learn how to be better facilitators for our respective learning communities we're working with. Each of these learning communities goes through and investigates research-based literature on topics like effective teaching practices, since that's our underlying goal here. Faculty that are currently teaching will pilot strategies in their classrooms with the support of their fellow participants. It becomes an excellent way when you try something new and it doesn't go well and you just sometimes need events or need to get advice from someone else. That's what the structure of the learning community can help with and give people an opportunity to revise and move forward, just like we would expect our students to do. The chairs have additionally examined best practices for recruitment, hiring, and the evaluation of faculty, both with diversity, inclusion, equity, and social justice in mind, but also the role that non-traditional teaching strategies can have on faculty teaching evaluations. We know there's been a lot of work in that area about what student evaluations mean or don't mean, and how we can best evaluate teaching. So that was one of that's an aspect that the chairs have gone through and taken a look at. Our learning communities are generally sustained experiences. So the new faculty learning communities have typically worked for a year together. Our STEM learning communities, it's depended on which type of learning community it was. Our part-time, we had one learning community explicitly for part-time faculty so that they didn't have to worry about any sort of unintentional power structure of being there with full-time faculty. Part-time faculty have always been open to join any of our STEM faculty learning communities, but we found that for a variety of reasons they were more hesitant to come and join. So we wanted to create a space just for them so that they might be more comfortable. So that was a 2-year community that just ended this past academic year. We've got a current one going that is going to be a commitment of 1 year with the possibility of extending to 2 if faculty decide that they want to go through and do that. Our chair learning community actually started as just a single-year community, but after that year, our chairs actually asked us to continue it. So that started at the very beginning of our grant and has continued since. Normally these communities meet once a month for 2 hours, or under COVID we've switched many of them to meet maybe for an hour twice a month, so that we have a little bit less time on Zoom and more breaks. The chairs have been meeting a little less frequently now that COVID has hit and there's been more work put onto them, but they're still interested in continuing, even as new chairs have come and gone as well. And then our facilitator community was always designed to meet throughout the life of the grant, since that's both our project team meetings and a place for us to learn to improve our own facilitation. In addition to these faculty learning communities, in order to support the community of practice model, our project team has responded to the needs of the community by creating some additional mini FLCs. So these were faculty learning communities designed to only last for about 6 months, with specific topics based on courses that faculty were planning to teach under our new semesters. So we recently went through the quarter semester conversion. Our first semester was this past fall. So in preparation for that, we had 3 learning communities, one based entirely on large lectures, one based on freshman seminars, which was new for us in our semester curriculum, and one based on writing intensive courses, generally within the major, which was also something new in our semester curriculum. In addition to these mini FLCs, we held remote teaching institutes when instruction moved online due to the pandemic. And we coordinate with other campus initiatives, such as our NSF Advanced Grant related to faculty recruitment, hiring, and evaluation, our Department of Education A for Us grant on STEM advising, and other initiatives as they've come up. We're towards the beginning of our 4th year out of 5 years of what started with about 10 faculty has grown to include 30% of all College of Natural Sciences faculty, 50% of College of Natural Sciences tenure-line faculty, and 75% of STEM tenure-line faculty. I'll note that the College of Natural Sciences includes the traditional STEM disciplines as well as the departments of nursing, health science, and kinesiology. And we'd like to thank our Dean, Sastry Pantula, and the university for supporting the non-STEM College of Natural Sciences faculty so that they can also participate in our Issues X activities. In the 2019-2020 academic year, we saw that 70% of courses, STEM courses with high DFW rates had a decreasing DFWI rate. So even though the rate may have been high, it was lower than it had been historically. So we're seeing those rates start to decrease. But we also recognize that the combination of our switch to online instruction this past year and the switch to semesters this past fall, because most of our curriculum has changed, is going to make future comparisons a little bit more difficult. But in our final year, we plan to examine the graduation rate trends over the grant period, as well as student attitudes towards instruction. So we have a lot of baseline surveys and data that we collected at the beginning of the grants, and that we'll examine at the end. Through the 3+ years that we've been working on this grant, and 5 if we include the earlier one, our university and our college has gone through multiple administrative changes. And while this project does benefit from the generous support that our college and university has provided us, we recognize that much of the progress that has been built upon our own relationships with other faculty across the college. This work has provided an avenue for us to get to know our faculty colleagues across the college. And over time, we've built amazing relationships with each other that I don't think would have happened without this work. Trying to meet and get to know faculty literally across campus, even though they may be a very connected department, is hard, and this has provided that sort of regular meeting time to build upon each other. This sense of community is central to the community of practice model, and we've noticed over the course of this project that it is exactly these relationships and the trust that come with them that has been key to our success moving forward. While we've had faculty of all ranks join our community, we found that the new tenure-line faculty as a group to be the most enthusiastic about the work. Supporting these faculty connects them with each other, with other faculty in the university early on, aiding in faculty retention while also helping progress our institutional transformation. And I'll also add that since we've had the additional workload of our semester conversion and the pandemic, that of course has been a negative contributing factor to making time for this type of professional development. Our next steps is we currently have a STEM faculty learning committee on culturally responsive teaching. The interest was so great we actually had to split into 2 cohorts, so we have one that just started and another that will start this fall. And we're looking forward to starting a CSU-wide faculty learning community in the next academic year. So to summarize, our Issues X project has created a community of practice within our College of Natural Sciences based on effective research-based teaching practices in order to improve student learning and success for our STEM students. The combination of our faculty learning communities and other informal activities has created a grassroots faculty-based path to institutional transformation in our college's approach to teaching and learning. So with this, I'll thank you and pass it back to Dr. Gomez.
Thank you, Carol, and everyone for really some excellent presentations. Your work's all fascinating and exciting, and it's really great to have you as colleagues within the CSU. Unfortunately, we're running a little late, so we won't be able to go to a Q&A today. Speaker contact information is provided on the next slide. For more information on any of the presentations, please contact the speakers, as they would love to either collaborate and certainly talk about their work, or potentially work together for a future proposal opportunity. In addition, a link to the webcast will be made available shortly on the STEMnet website. We'll be also emailing a feedback survey to our registrants. Your feedback's important to us so we can improve and as well as offer other excellent webcasts in the future. For information on this webcast, please contact Monica Alarcon or myself, and previous webcasts can be found on the STEMnet website. And finally, since our last webcast in early December, much has occurred in the country, irrespective of one's political leanings. We can all agree that events stemming from the November election will continue to shape the nation for years to come. While many may single out the previous resident of the White House as the cause for the chaotic nature of the present, he was but one product of deep-rooted divisions percolating for years in American society, and which, for too long, many turned a blind eye to. To address the systemic problems and their causes would likely be uncomfortable to many, who either disavow their existence and or play some role in their existence. Personally, I saw January 20th like listening to Sinatra sing Night and Day. It was as if a huge weight was taken off the back of our country, one which had weighed us down for 4 years. It was great to hear President Biden state our administration will lead with science and scientists, totally free from political influence, with federal agencies whose decisions are based on science and science alone. Furthermore, he said his administration would focus his scientific efforts on 5 main issues: the pandemic, the economy and economic equality, the climate crisis, technological and industrial leadership, and restoring trust in science. It is heartwarming to now have an adult in the White House, and we should rest a lot easier at home knowing that at least for the next 4 years, the only cringing tweets we might hear will be from birds outside our windows. So let's move forward and do what we can to support our students, their dreams, and their ambitions. We all chose to be part of a great educational system in the CSU that prides itself on providing opportunity for many, and for some who never felt they could attain a college education, let alone a college degree. Like I have said before, hope does spring eternal in the CSU. To all of you, be safe. May the rest of your day be a happy one. And I now turn it over to our own excellent Jennifer Wicks for keeping me sane and keeping all of this these webcasts in line, and for her few closing remarks too.
Thank you very much, Frank. It's always a pleasure to work with you on these webcasts, and of course Monica Alarcon behind the scenes as well. I just want to make sure everyone is aware that there is a survey that Monica has placed into the chat pod there for everyone to access. We appreciate all of your feedback as we move forward through this series, and also we have the STEMnet community listserv available on the screen as well. Please do access that if you're not already involved and added to that, if you haven't joined it yet. And of course the Facebook group for all the conversation. Thank you, Monica, for that. And some notes there also on the slide about the Virtual Research Cafe 10.0 on February 19th, and the STEMnet March webcast coming up on March 10th. So we look forward to seeing everyone back again right here, same link, same channel, with more excellent, incredible presenters and researchers from across the CSU. So again, we want to thank all of our excellent presenters today for their time, their knowledge, and their ability to share all of their body of work. So thank you so much for being here, and wish you all a great rest of the day, and we'll see you again in March. Thanks, everyone.